In this and the next segment, we're going to see two important applications of depth-first search. The first one is finding strongly connected components in directed graphs. So what's a strongly connected component, or an SCC for short? We'd say that two vertices u and v are in the same strongly connected component if there's a path. Remember, this is a directed graph, so if there's a path from u to v and from v to u. These should be directed paths, of course. Now, this kind of relationship between vertices, two vertices being in the same strongly connected component, is what is called an equivalence relationship. Equivalence relation. So what's an equivalence relation? You may have studied this earlier in your life somewhere, but basically an equivalence relation is a kind of binary relation that has three properties. The three properties are that every object is in relation with itself. That's called the reflexive property. The second property is if u is in relation with v, then v is in relation with u. This is the symmetric property. And the last one is the transitive property, that is that if u is in relation with v and v is in relation with w, then u is in relation with w as well. So let's see why two vertices being in the same strongly connected component is an equivalence relationship on vertices. Well, it's clearly reflexive because there is the path from any vertex to itself. From a vertex u to itself, there's a path of length 0, and that goes both ways, of course. So u is in relation with itself. That's the reflexivity for any vertex u. Symmetry, the definition is basically symmetric already, because in order for u and v to be in the relation, there must be a path from u to v and from v to u. So if u is in relation with v, both of these paths exist, and that means that v is also in relation with u. So symmetry comes automatically from the definition. Transitivity is the only interesting part. What we want to say is that if u and v are in relation, meaning there are paths from u to v and v to u, and v and w are in relation, which means that there are paths from v to w and w to v, then u and w are in relation. And that's not hard to see. Because there's a path from u to v and there's a path from v to w, you can concatenate or append the second to the first, and you get a path from u to w. Well, this may not be a simple path, but we've seen already how if you find any path at all, you can cut out the repetitions and make it into a simple path. So there's a simple path from u to w, and the reverse direction is just as easy. So basically, that means that u and w are in relation. So when these three things happen, when a relation is reflexive, symmetric, and transitive, we call it an equivalence relation, and it basically divides the objects on which the relation is defined, in this case the vertices of the graph, into sets, which are called the equivalence classes, so that two vertices are in the relation if and only if they are in the same set. Now, the strongly connected components are defined per equivalence class of this relation. All the vertices in one equivalence class and all the edges between them are one strongly connected component. Okay? The whole graph is called strongly connected if all of the vertices of the graph are in relation with each other. Okay, now how do we find the strongly connected components of a graph? There is an algorithm called Costa algorithm for finding strongly connected components that we will see next, and it uses DFS in a key way. And one of the things I want you to think about as you hear this algorithm, which is somewhat complicated, more complicated than many that you've seen, is that it is not at all obvious why it is correct. And perhaps you will appreciate the need, as we get to more and more complex algorithms, for coming up with proofs of correctness of these algorithms to be confident that what we've done is the right thing. Okay, how does Costa algorithm work? So it does a DFS on the graph G and keeps track of the finish times of the vertices. Recall what finish times and start times are. We defined them in the last segment. It keeps track of the finish times, and it creates a list L in reverse order of the finish times, meaning that the vertex that finishes first is going to be put at the end of the list, and the vertex that finishes last is going to be put at the beginning of the list. So let's see this in progress on this example. We start the DFS at vertex 1 in this graph. And from 1, it say goes to 6, and 6 becomes gray, nothing is finished so far. From 6, we go to 8, and 8 becomes gray, and there's still an outgoing edge from 8, so we continue on to 7. At this point, the only outgoing edge from 7 is to vertex 6, which we have seen already. So it's gray. That means that 7 is finished. And so it becomes black, and we put it at the end of the list. Remember, the vertex that finishes first goes to the end of the list. And continuing on, we come back to 8, and we find that there's no more outgoing edges. 8 is finished, and then 6 is finished, and then 1 is finished. Now there are still vertices that are white that are left, and we cannot reach them from 1. So we start DFS at another vertex that's currently white. This will be vertex 3, for example. So that becomes gray, and we continue on in the familiar manner of DFS. And you see that at 4 has just become gray. There are no outgoing edges to vertices that are white. So 4 is finished. And then now going back to 2, which is where we came from, when you go back to 2, we find there are no outgoing edges anymore. So 2 is finished, then 5 is finished, and then 3 is finished. So we've stored the list L, the set of vertices, in reverse order of finish times. The one that finishes last is first on the list. So after we've done this, Costa-Raju's algorithm reverses the directions of all the edges of the graph. As you can see, this is the graph with all the edges in reverse direction. This new graph is called the transpose of the original graph. And we run DFS on the transpose graph, but in the order specified by the list L. The list L, again, recall, was arrived at from the first DFS in reverse order of finish times. And we used that order to decide which vertex to start DFS from at each point. So we will start DFS now from vertex 3. And each time we need to start DFS again, because we can't go anywhere else, we found one strongly connected component and we output it. So we start at vertex 3, and we find that it has nowhere to go. So 3 is a strongly connected component by itself. Next, we try a DFS from vertex 5. And from 5, we can reach vertices 2 and 4, actually 4 and 2. And so those 3 form a strongly connected component, and you cannot get to any other vertices from there. So then we start, after we've done with 5, 2, and 4, we start with the next vertex on the list L, which is vertex 1 now. So we start here. And we see that we can reach all the other vertices from 1 to 8 to 6 to 7. So those form another strongly connected component. So the claim is that the strongly connected components found by Costa-Raju's algorithm are 3 by itself, 5, 4, 2 as one, and 7, 6, 8, 1 as another. So these are the 3 strongly connected components found by Costa-Raju's algorithm. And here's the pseudocode for this algorithm. I will let you look at it, but basically we've explained the working of the pseudocode already. Now for the correctness, because this does seem a little mysterious. Why is this algorithm correct? And the correctness is captured by the following lemma. It makes the point that if you look at 2 vertices u and v in the list L, remember L is the list of vertices in reverse order of finish times on the first DFS, on the original graph G, not on the transpose. If u comes after v in L, then either there's a path from v to u, or there is no path from u to v. Okay, I'll let you read the proof, but let me give you a sort of an intuitive explanation for why this lemma is correct. So u comes after v in L. That means u finished after v. So u comes after v, I'm sorry, v finished after u, because it's in reverse order. So v finished after u. So what does that mean? So v started at some point, maybe while DFS of v was active, so we were between the start time and the finish time of v, we encountered u. So there are 2 possibilities here, basically. So here is the timeline, and say this is the start point of v. Start of v occurs somewhere on the line, and then here is the end of v, occurs somewhere else. Here's the end of v. Now, so we know that u finished before v, right? U finished before v. Now it could be that u started in here, so u started here, and then it went up to here, and then u finished here. So the finish of u was, the end of u was here. If this happened, what do we know? That means we know there's a path from v to u. So either u started after v started and finished before v finished, and therefore there's a path from V to U. Or the alternative is U started here and finished here. That means that U was started and finished before we even started with V. And the question is, why did the DFS of U find V? So in the first case, when the interval for U lies within the interval for V, then we find that there must be a path from V to U, because while we were doing DFS of V, we found U, there must be a path from V to U. Now in the second case, if U started and finished before V, then while we were doing DFS of U, we did not find V, which means there must not be a path from U to V in the original graph. So those are the two possibilities. Whenever we see that U comes after V, either there is a path from V to U, or there is no path from U to V. So that's what we conclude from the properties of DFS and our list L. So in the second DFS, we assign each discovered vertex to the same strongly connected component as the root of the DFS search. We need to make sure that each of these assignments is correct. So when we assign the vertex U to the same strongly connected component as the root V, we have by definition found a path from U to V in the original graph. What this is saying really is that we found a path from V to U in the transpose graph, and therefore that corresponds to a path from U to V in the original graph. So all we need to check is that there's a path from V to U as well. But the point is this: if U is undiscovered when we visit V, U must come after V in L. So, but the lemma says there are only two possibilities. Either there is no path from U to V, or there is a path from V to U. So we already know that there is a path from U to V. That's what we said in the last bullet point. And so that rules out one of the two alternatives. So there's, if you look at this either or statement, there's no path from U to V, or there's a path from V to U. And because we know there's a path from U to V, we've ruled out this alternative, which means we conclude that the other alternative must hold, which is there is a path from V to U. We already have a path from U to V, and that proves that U and V are in the same strongly connected component as the algorithm decides they are. So the algorithm is correct. That's the sum of that's the final sort of analysis of this algorithm. And you can see that it was not obvious at all why it was correct, and we had to go through some good understanding of DFS properties in order to argue that the algorithm was correct.